Welcome to Chemistry Made Simple. Today we are going to look at the part 4 of the volumetric analysis. In fact, I'm very happy you have joined me up to this far. Today we are going to have a very special lesson. Thank you. Volumetric analysis part 4. Today we are going to look at a very simple question where we are going to go through numerical analysis of the quantitative analysis. Join me to the bench to look at some few observations and then also make some few conclusions, deductions, and then also for us to help us know whatsoever thing we are going to do at the end of the day. We are going to solve the problem on the board, all right? But let's look at some analysis over here first before we go to the board. Now we have a very simple titration where we have the results on the bench over here. We have 3 conical flasks, and within the 3 conical flasks, we have 2 different solutions meshed up together, giving us a particular endpoint. For this 3 conical flask contains 2 solutions, a strong acid and then a strong base. We used metal orange as the indicator in these samples. We use metal orange as the indicator. In fact, at the end point, we are expecting the solution to be neutral at end point. Metal orange will turn orange at end point because the solution will be neutral. Now we also have a distinctive form of titration also over here, which is also a strong acid and at the same time a strong base in here. So we have 2 solutions, a strong acid and then a strong base again. This time we used phenolphthalein as the indicator. Phenolphthalein in the base was pink, deep pink, and then we know that at end point the solution will be neutral. Phenolphthalein in a neutral solution is colorless, so the expected end point color is colorless as we see it over here nicely. Now to the board. Bn is a solution containing 7.20 gram per dm cube of impure tetraorthosulfate 6 acid. Cn is a solution containing 5.00 gram per dm cube of sodium hydroxide. The instruction is put solution Bn into the burette and titrate 25 Cn cube portions of Cn with Bn using phenolphthalein as indicator. Record the volume of your pipette, tabulate your burette readings, and calculate the average volume of the acid used. From your results, calculate A, the concentration of tetraorthosulfate 6 acid in mole per dm cube. B, the concentration of pure acid Bn in gram per dm cube. C, the percentage purity in Bn. D, the percentage impurity in Bn. Now we have been given the atomic masses for the various elements that could be seen in the chemical formulas. Now, this is our problem for today. So the part 4 of this section of the volumetric analysis, we are going to look at this simple problem and then how to resolve to it. Now we have tetraorthosulfate 6 acid, which is solution Bn, and then we have sodium hydroxide, which is solution Cn. Sodium hydroxide is a strong base. Tetraosulfate acid is also a strong acid. Therefore, you agree with me that the reaction is between a strong acid and then a strong base. Therefore, from theory, the expected endpoint, we expect the solution at endpoint to be neutral. So it means that at endpoint, the solution will be what? Will be neutral. Therefore, there comes the question, what will be the color of the phenolphthalein at endpoint? Before we can answer that question perfectly, we should know the color of phenolphthalein before we started the titration. Where will the phenolphthalein be placed? In fact, from our titration, we are going to pick 25 centimeter cube portions of CN. And then we will transfer it into a conical flask. And then add 2 drops or 3 drops of phenolphthalein. Phenolphthalein in the basic solution is deep pink or pink. Now, that is the initial color that we will see before we start the titration. Deep pink or pink. Now, we have already said that at endpoint, the solution will be neutral. If the solution will be neutral, from theory, the color of phenolphthalein in the neutral solution is colorless. Therefore, we know that at endpoint, we are going to have a colorless solution, as I showed you earlier. Now, this is how we solve the problem on the board. For my various students and then candidates, in fact, you don't just begin by drawing the table, the experimental table. No. Remember, from the question, he has given you an instruction, a specific instruction. He said, record the volume of your pipette. So it means that one is very, very necessary. Why? From the various schools and then from the various points where you are located, we don't know which volume of pipette you used. So it is only when it has been indicated on top of the table or on top of your experimental table, then you'll be able to determine which volume of pipette you use or the capacity of the pipette used. So I'm going to first record the volume of my pipette, which is very, very necessary. So 25 cm cube. I use 25 cm cube. Indicator used is also necessary. Phenolphthalein. Now I can proceed to draw my table very nicely. So I want to draw my table. So we have direct readings, final reading, initial reading, and then volume of acid used. You can add in CMQ. This one in CMQ. So we want to get the volume of the acid used. You just deduct this from that, and that will give you the volume of the acid used. You deduct this from this. So you deduct the initial from the final. So whenever you want to get the volume of the acid used, you deduct the initial from the final. It depends as to how you want to start your titration. Sometimes, in fact, you can fill the burette in such a way that you pass the 0 mark and then you flush out the air bubbles, so that at the end you reach what? The 0 calibrated what? Mark on the burette. Sometimes too, some people they want to fill it to the 0 mark and then they flush out the air bubbles, where at the, in fact, before they start their titration, it will not be 0.00 by then, because the content of the air bubbles that they flush out has also taken some small portion out of the volume of the burette, from the burette. So they can start their initial from where they indicated that they want to start their initial volume from. So the initial reading depends on you. For mine, I started from 0.00. In fact, I always fill the burette to the higher mark, or the mark above the calibrated mark on the burette, and then I flush out the air bubbles. So at the end, I always expect that the air bubbles will be flushed out, and then we'll get so that I can get a calibrated mark of what? 0.00 at the end. That is how I started mine. So my initial readings were 0.00 throughout. Now we have the table. So we have the table nicely. What is left for us to do is to calculate or to determine the average titer. In fact, we have already discussed how to calculate for the average titer, of which we said we choose values which are so close. In fact, the difference between the values that you are supposed to choose is supposed to be plus or minus 0.2 or plus or minus 0.1. So looking at this one, for my volume of the acid used, here I have a difference of plus or minus, that is 0.1, plus or minus 0.1. So which means I can choose any of them, any of the two values, and then what? Any two from the three values, and then what? Use. So let's say I want to pick this one from the first reading and then the second reading. So average titer. So it's left for us to make choice over here. Volume of the acid used. We have already spoken about consistency. Looking at the consistency level of the volume of the acid used, you can see that the difference over there is what? Plus or minus 0.1. Therefore, you can make an attempt to choose only two. You are not wrong. You can also pick the 3 and then find it average. That one you are not wrong. For me, I will choose all the 3 and then find it average, because looking at the consistency level, it is just plus or minus 0.1. So I choose all the three. Now, all the three added, divided by 3, will give me the average. And then to give me an average of 29.80 cm3, which is my average titer. Now I have been able to determine the volume of the acid that was able to neutralize the 25 portion cm3 of the Cn, which was pipetted. Therefore, I will be able to further make analysis. So I'm going to start with the analysis from the first question, which is A. The A part of the question says, the concentration of tetraosulfate 6 acid in mole per dm3. Now, let's look at the general idea concerning the question. Bn is a solution containing 7.20 dm3, gram per dm3 of impure tetraosulfate 6 acid. Cn is also a solution containing 5.00 gram per dm3 of sodium hydroxide. Now, from the question, we can say that one of the solutions is not standard. One is standard, one is not standard. In fact, the general idea or the general aim for titration is standardization. It's for us to standardize one solution. So it means always one of the solutions that will be given out of the two, one of them is standard and then one of them is not what? Standardized. So with the help of the one which is standard, we'll be able to standardize the other one which is what? Not standard. So from the question, Bn is an unstandardized solution. Cn is a standardized solution. Therefore, if we are supposed to do analysis on the concentration of the tetraosulfate 6 acid, which is not standardized, we can use the standard solution, which is sodium hydroxide, to do that form of what? Standardization. Therefore, when we say something is standardized, in fact, what you should critically think about or what should come into mind is that there is every bit of information on one of the solutions, which is termed as what? Standardized, to calculate for any form of analysis that is supposed to be made on the other solution. That makes that particular solution what? A standard solution. So when you look at solution Cn, there is every bit of information on solution Cn to determine anything that you want to determine about solution Bn. Therefore, it makes solution Cn a standardized solution. But when you consider that of Bn, we have some little form of information on solution Bn, alright, but it is not complete. So the incompleteness of Bn makes what? Bn an standardized solution. Now, we have been given the mass concentration of solution Cn. So here, mass concentration of Cn. So we have the mass concentration of solution Cn, which has been given nicely. Now, what again can we deduce? Molar mass. Molar mass of Cn. So, molar mass of Cn, bracket Mr, and is NaOH. So, molar mass of Cn, which is mRNaOH. Now we can find the molar mass. So, this is how to find the molar mass. Sodium has been given MR NaOH 23.0 times 1 plus oxygen 16 times 1 plus hydrogen 1 times 1. So we have 23 plus 16 plus 1. So molar mass which has been denoted by that. 23 plus 16 plus 1, which is 40. So it's 40 grams per mole. That will be the molecular mass for that. Now we have been able to determine the molecular mass for that. Because we have been able to determine the molecular mass, then it means that we have two parameters. Since we have two parameters, what comes into mind? We know that there is a formula that says that if you want to convert mass concentration into mole per dm³, then mass concentration of that substance is equal to the mole per dm³ concentration of that substance is equal to the mass concentration of that substance divided by molar mass. So we have that in mind. But concentration in mole per dm³ is equal to concentration in gram per dm³ divided by the molar mass. So concentration in mole per dm³ of NaOH and the mass concentration of NaOH divided by molar mass of NaOH, this manner. So it means we can pick the mass concentration, which is 5.00 gram per dm³ divided by the molar mass, gram per mole. At the end, what do we have? 5 divided by 40, which is, so concentration in mole per dm³ of NaOH is equal to 0.125 mole per dm³. So this is the concentration of the base. This is the concentration of the base. Now we have been able to determine the concentration of the base in mole per dm³. What comes into mind? The analysis. Remember that we are still going through numerical analysis. This implies that 1000 cm³ contains 0.125 mole per dm³ of this. So 1000 cm³ contains that. But you agree with me that the volume of the base that was used or that underwent what neutralization wasn't 1000 cm³. It was only 25 cm³ portions. So this means what will be 25 cm³ contains? So 25 cm³ contains how many moles? Remember, we are going to make analysis on what? On the moles. So this means that 25 cm³ divided by 1000 cm³ multiply by 0.125 mole per dm cube. Remember, we are dividing by dm, so dm will cancel out. So it means that at the end our unit will be in what? In moles. So we have 25 divided by 1000 times 0.125. So at the end we have, so this one will be moles of NaOH will be 3.125 times 10 raised to the power negative 3 moles. So that will be the moles of the base. That will be the moles of the base. Now, let's put forth the equation of the reaction. For the equation of the reaction, we have H2SO4 plus NaOH will produce Na2SO4 plus H2O. So you balance with 2. Then it means that B2 there. So we have a balanced equation in this form. So from the equation, we can see that 1 mole of H2SO4 was equivalent to 2 moles of NaOH. So 1 mole of the acid reacted with what? 2 moles of the base. Now we have moles of the base. And you know moles of the base. So what will be the moles of the acid contained in? We don't know. That one is question mark. But we know that it contains 3.125 times 10 raised to the power negative 3 moles of NaOH. Then what will this one contain? It means at the end you have 3.125 times 10 raised to the power negative 3 times 1 mole of H2SO4 divided by 2. So we have it in this form. So we know 2 moles of that is equal to this. Then what will this one equal to? So at the end, this one divided by 2. So we have moles of the acid will be 1.5625 times 10 to the power negative 3. So we have these moles of the acid reacting. So that is the moles of the acid reacting. Now we have been able to determine the moles of the acid reacting. Remember, this one is reacting in the context of 25 cm3. That is in a volume of what? 25 cm3. These moles were in 25 cm3. It is equivalent moles, so which means this mole also reacted in what? In the volume of what? In the average titer. In the volume of what? Of the average titer. So it means we have, this implies that you have 29.8 cm3 contains 1.5625 times 10 to the power negative 3 moles. Then what will be in 1000 cm3? What will be it contain in 1000 cm3? So is 1000 cm3 divided by the average titer multiplied by at the end it will be mole per dm3. That will be the concentration. So concentration in mole per dm3. So that will be the answer times 1000 divided by 29.80, which will be 0.052 mole per dm3. So we have been able to determine the concentration of the acid. So therefore, so that is the concentration of the acid in mole per dm3. Now B. For the B, he said concentration of the pure acid. Concentration of the pure acid, Bn, in gram per dm3. Now this is very, very simple. Once you have been able to determine the concentration of the acid in mole per dm3, it is just a conversion factor. So we have our concentration in mole per dm3. We are going to convert to gram per dm3. So we will use our formula. Concentration of the pure acid. Concentration of the pure acid. To find the concentration of the pure acid, we have our formula. Concentration in mole per dm cube is equal to concentration in gram per dm cube divided by molar mass of the substance divided by molar mass of the substance. So concentration in mole per dm cube of the acid. You have that concentration in mole per dm cube of the acid, which is 0.052 mole per dm cube is equal to concentration in gram per dm cube, all divided by molar mass of the acid. So molar mass of the acid which is H2SO4 will be H is 1 times 1 times 1 plus sulfur is 32 times 1, oxygen is 16 times 4. So we have 2 plus 32 plus 16 times 4, which is 64. So plus 32 plus 2. So we have 98 gram per mole. So that is the molar mass of the H2SO4. Now we have the molar mass, so we can put the molar mass of the acid there. So this implies that we have 0.052 mole per dm cube is equal to gram per dm cube divided by 98 gram per mole. So this one we use cross multiplication. So gram per dm cube will be equal to 0.052 times 98. So at the end we have 5.096 gram per dm. So therefore the concentration of the pure acid is 5.096 gram per dm. So that is the concentration of the pure acid. So this is the mass concentration. When you compare the mass concentration of the pure acid to the mass concentration of the impure acid, you see that there will be a difference. You can see a very vast difference between them. So we have been able to determine the second part. We have been able to go through the analysis for the second question, which is the concentration of the pure acid in gram per dm cube. Now we are going to make some simple analysis on the differences between the mass concentration of the impure acid and the mass concentration of the pure acid. That I want to wrap off this portion I want to rub off this portion so that I'll be able to go through that analysis. Okay, so we are going to make analysis. In fact, I was rubbing the board so that I can make analysis on the mass concentration of the various substances. Now, we are going to begin with that of the tetrasulfuric acid. So, the mass concentration of the pure of the pure acid, we had that to be 5.096 grams per dmq. Mass of the impure acid, 7. So we have mass concentration of the pure acid, mass concentration of the impure acid in that manner. Now we can determine the amount that remains what? Unreacted, even from that, on that context. Now let's look at what we want to do over here. Now we want to determine the third part of it, or make analysis on the third part of the question, which says the percentage purity in Bn. Percentage purity in Bn. So C. Percentage purity in Bn is equal to the mass of the pure Bn over mass of the impure Bn times 100. So mass of the pure Bn over mass of the impure Bn times 100 will give us the percentage point. So we have the mass of the impure, the mass of the pure, which is 5.096, and then 7.20 times 100. So we have 5.096, 7.20. So we have here 70.77, 78%. So that is the percentage purity in Bn. Now, the D part, which is the percentage impurity in Bn. We have been able to determine the percentage purity in Bn, and so the percentage impurity, we know this is the mass of the pure, this is the mass of the impure. So if you deduct this portion from that, you get the mass of what? Of the impure substance. You get the mass of what? Of the impure substance. So D, percentage impurity in Bn. In simple put, we have to find the mass of the impure, that is the mass of the impure in Bn, and then divided by the mass of the impure again, the total mass of what? Of the impure. So mass of impure in Bn, that is impurity in Bn, divided by total mass of impurity times 100. You know, mass of impurity in Bn, mass of impurity in Bn will be 7.20 minus 5.096. So at the end, 7.20 minus 5.096 is giving us 2.104. That is gram per dm. So that is the mass of impurity in Bn. So we will further continue with our analysis. If this is the mass of impurity in Bn, then it means we can find the percentage impurity in Bn to be 2.104 divided by the total mass of impurity, which is 7.20 times 100. And we have 2.104 and 7.02 times 100. So which is 29.22%. 29.22%. Now, this is the percentage impurity in Bn. Or systematically, or percentage impurity in Bn could have given us 100% minus percentage purity in Bn. This also could have been used. So percentage impurity in Bn could have been 100% minus 70.78%, because that is the percentage purity in that. And our answer could have also result in the same thing. So 70.78, which is 29.22%, which would have been the same, which would have given us the same results. So in fact, that is how we can perform simple numerical analysis on the various forms of what solution that we have. Now, we have discussed today how to determine the concentration of a particular substance, a solution, in mole per dm cube. We have also resolved to how we can convert it into the mass concentration, which is gram per dm cube. We have also resolved to percentage purity, percentage impurity, and then so on. Now, that is technically about the numerical analysis on volumetric analysis. So when you talk about volumetric analysis, we are talking about these forms of numerical analysis and then the rest. Now here I use ratios and then the rest. In fact, we could have used formulas also to resolve to the various part and then the rest. But I prefer using these forms because it is very, very nice and then very easy. Looking at the ratios, how we linked the ratios with the equivalent moles and then the rest. I believe you have been taught. I believe you have learned a lot from the sample question that we solved. Thank you, and then you are highly welcome to Chemistry Made Simple. See you in my next tutorial. Bye.